Candace is a prof whose fascination with the physical world has opened her curiosity about a wide range of things, from stars to cellular machinery to chemical reactions and fields and subatomic particles. Perhaps, though not necessarily the stuff that we think about every day. Her doctoral work was in condensed matter physics, and her research has focused particularly on how large biomolecules work, how they communicate with one another to perform their function. And she has had her work published in a range of journals and done presentations in a variety of international settings. Perhaps as importantly, Candace is a lover of poetry and literature. She believes intimately that science and imagination go hand in hand. She is an alto in the St. George Anglican Church Choir. She's a faculty member here, deeply committed to teaching undergraduate students, a love of science, and an openness to think about the big questions that surround all of us. So we're delighted, Candace, that you have consented to open this face-to-face conversation on the topic. It's not only about atoms, embracing a science of complexity. Following Candace's presentation, I will come back up here and facilitate some conversation with Candace and amongst ourselves. And so I invite you, as she is speaking, to be thinking about, I wonder about this. Please join me in welcoming Candace.
Am I on? Yeah. Good evening. Thank you, Terry, for the nice introduction. In case any of you are wondering what condensed matter physics actually is, well, basically, I studied chunks of material that just kind of sat there, but became really, really fascinating when I learned how to look at them the proper way. Just to fill that in for you. So first, I thought I'd start with a word on why I chose science as a career. It's basically this, like the poet John Dryden said, there is absolute joy in looking and comprehending, and that's one of nature's most beautiful gifts. Secondly, you might wonder exactly what is physics. I'm sure you all have a general idea, but some of the questions that fascinate us as physicists are things like, how does the sun keep on shining? When we see light streaming in through the window, we might ask, well, what is the nature of that stuff that seems so different from everything else around us? Or, what are the basic building blocks of matter? Or if we look at the clock, we sort of get teased at the elusive nature of exactly what time is. So a physicist is obsessed with understanding what the nature of the universe is. And when you study physics, you launch on a never-ending quest for understanding this fascinating universe that we inhabit. And to attempt to understand questions like this, the first thing that we do is we have to set up models, pictures of how we can understand phenomena. I'm sure you all have heard of the story of Isaac Newton, one of the big pillars of physics, who supposedly was sitting under a tree one afternoon when an apple hit his head, and he thought, well, why does an apple fall anyway? So his answer to the question was, well, masses attract each other a certain way, and so you've got the big Earth and you've got the apple over here. There's a force between them. The apple comes toward the Earth. A few hundred years later, Albert Einstein, another towering figure of physics, said something completely different. He said the apple falls because the heavy objects curve space, and lighter objects then are attracted to the heavier objects because they fall in like a funnel towards them. So here you have two answers to the same question, why does an apple fall? But both of them create very, very different pictures of our universe. So today what I want to do is introduce you to a debate in science that has actually raged on for about 24 centuries, and it still continues. The question is this: can the entire universe be explained in terms of atoms? Or, if Humpty Dumpty is the universe and we break him apart, can we put him back together again? The debate is old, and we keep making new discoveries, keeping all these issues at the forefront of science. And what I will do is I will share 3 broad perspectives with you, but understand that there are actually many more shades in between these perspectives. And to frame the debate, I'll be wearing 3 different hats, literally. Well, actually, I'll be wearing 2 hats and a scarf, and I will speak in support of each viewpoint. So here's my first hat. You'll see it looks kind of like an engineering hat, and that's not an accident. So this is the first perspective on matter. So thoughts on matter really started with the ancient Greeks, who looked at all the variety of forms around us and wanted to know, if we want to ever understand the world that we live in, maybe we should try to take all the complexities out of it and just focus on the essence. What is really there? All the complexities, all the diversities kind of cloud the essence. And so for Plato, the key words in thinking about the universe were things like simplicity and harmony and symmetry and pure beauty. And then Democritus came along, and he was a key figure in our thought about matter at the time. Now, I don't know all that much about Greek society, but I do know there were a lot of philosophers, and I do know they had a lot of pottery. So I can picture Democritus sitting in Athens, perhaps, taking a piece of pottery in his hands and just kind of contemplating, wondering how many times he could break it in half until he got to that fundamental limit where it was no longer divisible. And that was actually Democritus's vision, that matter was grainy, and there was a point at which if you broke everything down far enough, you couldn't break it down any further. But once we reached that part and understood in great detail those little pieces of matter, we would be able to understand the whole. Because the whole is nothing more than the sum of the parts. Titus Lucretius, a Roman philosopher a few hundred years later, said the same thing, except maybe with a little bit more touch of humor. He said, all that exists are atoms and void, and the rest is just opinions. So let's fast forward to the 21st century. Turns out Democritus was right. There are fundamental building blocks. Now, we've known about atoms for a while, what we believe to be the smallest building block. But we discovered that what we thought was the smallest building block actually had smaller parts. Our view of the atom 100 years ago was that it was composed of electrons around a nucleus which contained protons and neutrons. But in the last 50 years, we've also discovered that those protons and neutrons inside the nucleus can be broken down into further pieces yet. They can be broken down into what are called quarks, and that electrons are just one of a family of what are called leptons. And so our fundamental particles right now are all quarks or leptons. And there are also force carrier particles that basically interact with other particles so that there's forces felt between them. And physics has identified 4 fundamental forces: gravity, electromagnetism, weak nuclear force, which, by the way, is why the sun shines, and the strong nuclear force, which is why we actually have atoms to start with. I'm sure you're all aware that protons, being positively charged, will repel each other. But in the nucleus, you've got all these protons snuggling together in a very, very small area. And they shouldn't be able to do that if we think about the proton charge repelling each other. But the strong nuclear force is actually the glue that holds those protons together at very, very small distances. So if it weren't for this force, then we would just have particle soup here. So, going back to the ideas of Democritus, if we take everything that we know about these particles, we should be able to put Humpty Dumpty back together again. Our test of that is whether we can predict what higher properties will be basically from the ingredients. Thus, physics right now thinks that all the phenomena in the universe can, in principle, be deduced from a handful of equations describing these fundamental particles. Albeit they're quite complicated, this is one of the handful. And this equation is part of what is called the Standard Model. It's kind of like the physics equivalent of to be or not to be. And embedded in all these equations are rainbows and flowers and zebras and everything else. Now, the modern movement in biology has also identified fundamental units built on the ultimate building blocks, but to biologists, the important units are genes and molecules. All of these components perform very, very important functions in our bodies. And so with this picture, we look at the universe as a hierarchy of stages, from atoms to molecules, molecules join to form cells, cells join to form tissues, tissues combine to form organs, et cetera, until you eventually get to the whole biosphere and then to the whole universe. But the idea isn't just that we have these levels. We all can see that we do. The idea is that we can actually explain all of the higher levels in terms of the lowest level, in terms of those fundamental particles. In fact, Francis Crick, who was a co-discoverer of the DNA molecule, said that the ultimate aim of the modern movement in biology is in fact to explain all biology in terms of physics and chemistry. And if we take that thought a little bit further, then what we have is, on the spectrum of disciplines, sociologists are just applied psychologists, psychology is just applied biology, biology is just applied chemistry, which is just applied physics. It's nice to be on top, and if there was a mathematician in the room, then they could have their little party. Now, for some reason, my colleagues just don't appreciate this. All the colleagues in other disciplines in mine don't really think this is the story. And they would tell me, okay, you think that the Standard Model explains everything, then how come you can't predict zebras with that equation? You know, you say in principle, but I don't actually see anybody predicting that zebras should exist. And I would tell them, well, okay, we haven't been able to yet establish the relationship between the whole and the parts, but that's maybe just we don't have enough computers. There's a lot of information in there. We'd have to have lots of computers to actually calculate that. Or our model isn't good enough yet. Our intellectual limitation is not allowing us to get to that place yet. But nevertheless, breaking everything down into these fundamental particles has been a very, very successful endeavor. It helps us to identify the underlying unity of matter, reveals the ultimate connectedness between all things. It helps us to predict and shape our world and aid in our own survival, whether it's through electronics or communications or treating disease or harnessing energy, etc. So to summarize, if I look at this rose through the eyes of the Standard Model, then I would say that everything about this rose can be explained in terms of leptons and quarks. And its entire beauty, from the rich color red, to the softness of the petals, to the internal sigh that I feel when I look at it, which all arises in my own consciousness, which arises from the sum of all the electrical and chemical properties of trillions of atoms in our brains. So we would say that the laws of physics describe everything. And our consciousness has brought us to ask the eternal question, why are we here? It's like the atoms are becoming aware of themselves. Now I will change hats. All right, so here's the next perspective. Well, I don't know about these reductionist physicists. I mean, I think what they're saying is if everything can be explained in terms of atoms, that's like saying that Hamlet is just a series of words on a page. Or that when I hear Brahms's German Requiem being played, it's just the series of the black notes on the page, even though it makes me cry. I discovered a painting not too long ago called Democritus in Meditation, by a painter named Salvatore Rosa in the 17th century. Now, in this painting, Democritus is sitting in a state of melancholy. He's got his hand resting on his head. In a setting of decay and destruction, there are animal skulls and bones in the foreground. And it looks as though the power of his analytical mind to see beyond his immediate senses has not brought him to a place of tranquility. Perhaps the opposite. And that's what bothers me, is when we have these extreme reductionist positions that I keep hearing about. Like that people are just robots whose main goal is to spread their genes. Or that civil disorder is just a manifestation of defective genes. Or even worse, maybe, a human life is a few dollars worth of chemicals. Or our sense of agency, our sense of having some control over our lives, what we call free will, is just an illusion. Or that love is merely a physiological response. So although I agree with Yoda that everything and everywhere physics is, I do question the statement that everything and everywhere and only physics is. I feel like if we think too much like this, we might get stuck in images of our world that leave out a lot of richness. I mean, how do we get from atoms, molecules, and genes to consciousness, dreams, and metaphors? When I look at this rose, I learn very little of it just by thinking about it in terms of atoms and molecules. For me, the rose has become a symbol of love and beauty. Its essential nature is my response to it. I think the reductionists are missing something. The rose is not just atoms, nor are we just atoms. We have heart and spirit and mind that transcends them. I tend to agree with a lot of the philosophers who say that our consciousness cannot be deduced from our knowledge of atoms or any other physical facts, that it's sort of the ultimate mystery. And because of our highly developed consciousness, we seek to discern and create meaning in our lives. Okay, so for the third and final perspective, this one's going to be a little bit in between the two. I'll start with a quote by Victor Weisskopf, who was a theoretical physicist in the early 20th century, who reminded us that our knowledge is an island in the infinite ocean of the unknown. And my question is, what if there is no such thing as the smallest building block? What if there is no possibility for even an absolute reduction? It may be that there are just more, we just don't know them yet. And in fact, nuclear physicists have postulated something called a preon, which they believe are possible subcomponents of quarks and leptons. Right now, they're strictly theoretical entities, but we might discover them one day. And if they are experimentally confirmed, is that where the chain ends? Or is it just like, is the universe like those little Russian nesting dolls, and we're just going to keep going lower and lower and never find the ultimate building block? The second part is, in practice, when you actually try to put Humpty Dumpty back together again, this proves to be quite challenging. I'll give you a few examples of what I mean. Imagine this little termite here. Now, I'm not a biologist, but biologists have told me that if you studied all that termite in great detail and knew everything about it and put them together in a group, you never would be able to predict on knowledge of this one termite alone that they'd be able to create these beautiful cathedral-like termite mounds. The building of this mound is what we call an emergent property. It's a new property that arises as a function of the whole thing, not of individual parts. So another way of saying that is that the whole is more than the sum of the parts. I'm going to give you a few more examples of what I mean by this, but let's just think about little mathematical objects for a second. If we take a point and take a bunch of points, we can arrange them into a line. And we know that we can do that. But the line now has properties that the point didn't have. The line has property of direction. Take a bunch of lines, arrange them, we get angles. You don't have angles at the level of the lower things. Take some angles, you can create surfaces. Take some surfaces, you can create volumes. So at each one of these levels in the hierarchy, you have new properties that you don't have at the lower level. And that's probably not so surprising. And that's the reason why we build things in the first place. We want to get new properties from things, put a few things together, and we get something new altogether. But the puzzle is whether those new properties can be explained in terms of the properties below them. That's the big question. Whether you can predict that those new properties at the higher level will actually exist. Now, you might argue for these mathematical objects, yeah, I can imagine if someone gave me a ball of marbles, I can imagine this line forming. But with other entities, this might be a lot more difficult. So take water. We know what water is, H2O, 2 hydrogens and an oxygen. And when H2O forms, it obtains properties that don't belong to hydrogen and oxygen. All those properties of the water molecule are rather unique to itself. That's what makes chemistry exciting. But these properties are very difficult to predict, and we cannot just take 2 hydrogens and an oxygen in a computer program, say, and predict what the properties of water will be. That's way beyond our comprehension. Or take water freezing into ice. Now, at this point, you might be saying, oh, this is like you're talking about paint drying here. And I would just remind you what I said. Physicists like to look at the most boring things, and in so doing, learn something profound about the universe. So let's talk about water freezing. So water freezes at 0 degrees Celsius. We all know that. But the question you should be asking yourself is, why is ice rigid and water is not? Both of these things are composed of the same molecules with the same forces between them. They're still feeling each other at a distance of 10 to the minus 8 centimeters. It's true that a liquid has a little bit more heat in it. Above 0, those molecules will jiggle around a little bit more, so they have a little bit more random motion. But that's true right up until that phase transition. When you hit 0 degrees, suddenly and abruptly, those molecules start to arrange themselves into an organized array. And the property of the whole goes from squishy and wet to solid and rigid. So the way that the molecules are organized entirely changes the properties of the whole thing. And it's the organization of those atoms that is key to producing those new properties. So let's just repeat that for a second. Before the phase transition, you have this. Random water molecules, you can't see any pattern in them. Right at 0 degrees Celsius, those water molecules suddenly cooperate and form an ordered structure like this. We call this a collective emergent property. It's a property that these ones didn't have. They do it on their own, so we call it a self-organization. And it's very, very sudden. This is like if you were on a public square somewhere and you had all kinds of people milling about, and suddenly, with no central commander to tell them what to do, they just decided to go in a row and all be equidistant apart. Just like that. And the really interesting part about this is that we cannot predict that this will happen by only considering a bunch of individual water molecules. If we try to take a bunch of individual ones and simulate it somehow, we don't get phase transitions. So what we have to do is we have to develop new laws in order to understand how that organization occurs. I'm not saying it's some kind of magical thing that's happening here, but it does require new laws. We can't explain it in terms of the properties of the individual molecules themselves. Or take magnets. A lot of your household magnets that you find on your fridge are made up of some kind of iron compounds. And if you imagine a pile of thumbtacks in front of you that you want to pick up, then basically the stronger the magnet is, the more thumbtacks you'll be able to pick up with it. But if you take your magnet and it's really, really hot, and you try to pick up some thumbtacks, you actually won't get any. And that's because the electron spins. Don't worry about what spin is, just worry about the fact that we're representing it by an arrow, and that if they look like this, you're not picking up any magnets. There's no magnetic properties at that point. But if you cool the magnet a little bit further, suddenly, again, at a single temperature, all those spins just go together. They cooperate as a whole unit. And you cannot predict the emergence of this behavior either just by thinking about individual spins. You have to use entirely new laws to explain that phenomenon. So the magnetic state, whether something's magnetic or not, is an emergent property of the collection of atoms. And so Phil Anderson, he was also a condensed matter physicist. He won the Nobel Prize in 1977. And he studied all kinds of systems like this, and he came to this conclusion. At each stage in the hierarchy, entirely new laws, concepts, and generalizations are necessary. And in order to learn what these are, or discover them, you need just as much inspiration and creativity to just as great a degrees in the previous one. So psychology is not applied biology, and nor is biology applied chemistry, etc., and so my colleagues get to keep their jobs. And now a skeptic would ask, is this a matter of principle, or is this a matter of practical impossibility? I mean, we don't really know. Is it that somehow the universe is such that new laws actually do come out of things, and they do transcend the properties? Or is it that our minds are just so limited in being able to discover patterns, or we don't have the computer programs able to do this? Well, we don't really know yet, but for practical purposes, we do decide that emergence exists. And in fact, most science cannot be done without some basic belief in this principle. Otherwise, the only people who would be doing anything useful would be the ones studying those leptons and quarks. And so what we do is we just sit and we watch the universe unfold and let it surprise us with fresh outcomes. So we don't actually know what the range of possibility is. So on that note, I just thought I'd briefly introduce you to some complex systems. These complex systems are actually very, very popular right now, and they're trying to study complex systems, you try to bring all kinds of scientists from different disciplines to look at them from different angles. And there's no single definition of what exactly makes a system complex, but one of them is this. A complex system is one that has large numbers of relatively simple entities that organize themselves without any sort of central command unit into a collective whole that creates patterns, uses information, and in some cases evolves and learns. So I'll just show you a few pictures of examples. One of these is, this is called emergent behavior with ants, because if they start over here on this leaf and they want to get over to this leaf, they are very crafty, and nobody understands how they do this, but they build an ant bridge from one place to another with no controller. Or sand dunes. You often see these beautiful, evenly spaced ripples forming in a sand dune, which you can't understand at the level of an individual grain. So all kinds of complex things happening. You've got the wind blowing over the sand, which would create a ripple, which would change the wind pattern, which would then affect everything else. Or why some fish school into spheres. How do they know how to do that? Or understanding the brain being made up of a bunch of neurons, and how many neurons have to be together to form a thought, and what kind of organization they have to have. A lot of people in computer science are studying things, or try to model this with something called a neural network. And it's believed to be a very complex system that has entirely new laws. And finally, if I have an internet connection, which I think I do, I can show you an example of a reaction that was discovered about 50 years ago that kind of started this ball rolling on complex systems. It's called the Belousov-Zhabotinsky reaction. And it's just a few chemicals put together in a petri dish and let the reaction starts, and you start to see patterns that you could never have anticipated. So you start seeing these nice concentric circles appearing in the fluid. And so now there's a whole, there's patterns evolving in here, and so you need whole new laws to describe this bigger emergent phenomenon. And so I would say all the king's horses and all the king's men couldn't put Humpty together again. Not yet, anyway. And so my perspective of ourselves would be that we are an animated collection of atoms and molecules, that consciousness is an entirely new activity that emerges in our brain because of the intricate way in which all of these physical chemical units that make it up have formed an organized complexity. Another way of saying this is that our consciousness and personhoods are an irreducible part of nature, out of which flows our emotions and our values, a part that affects the universe. And so just to summarize, complex systems are characterized by these words: networks, big intricate connections between individual units as opposed to individual things just adding up into a bigger thing. Dynamic, lots of changes as a function of time. Probability, being able to sort of understand the range of possible outcomes, but not specific outcomes. And the idea that we can maybe influence outcomes rather than control them. Simply because when you get complex systems, there seems to be an irreducible tangle of causes. You can't often point to one thing. And in case you're thinking that maybe this is all a bit academic, well, it turns out that in September 2009, there was actually a global science forum put on by the Organization for Economic Cooperation and Development called Applications of Complexity Science for Public Policy. And in this document, a whole bunch of scientists and policymakers came together to sit and brainstorm on ways in which these kinds of ideas might change the way that we do policy, the way that we set policy. And they identified things like the way that we think about the global economy, for instance. And sort of in a coincidence, a couple weeks ago, I was driving home and I was listening to CBC Radio 1, and they had an economist on there talking exactly about this. Also, prediction of major political events. Climate is definitely a complex system. Understanding how interactions of social, economic, and political assets might form communities that are either highly vulnerable to disasters or resilient to them. Pandemics, or how communications networks subject to a series of malfunctions might be made robust enough that they won't be so sensitive to one problem. And so I'll close by saying, giving you a quote by Stephen Hawking, who always reminds us to be humble. He says, "We are not angels who view the universe from the outside. Instead, we and our models are both part of the universe that we are describing."